We're going to use a balanced chemical reaction to be able to convert from mass of one of our reactants to mass of one of our products. And you might think, yeah, that shouldn't be so hard, but there's actually a step that's really, really important, which is that what this reaction is telling us is the relationship between the moles of each reactant and product. So for example, this reactant is saying you're going to take 6 moles of GZA, and remember, these are made up elements. These are not in our actual periodic table. You have to use your made up element chart here to do that. So we want to take our, moles of GZA. So it's 6 moles of GZA plus 8 moles of CG yields 4 moles of CG2A3 plus 3 moles of GZ2, right? Now, the reason that there's this in-between step is because if I say I have 5 grams of GZA2, we actually don't know right off the bat what that means in terms of moles. And there's no clear relationship between the grams of a reactant and the grams of a product. And just to remind you of why that is, remember that each of our, let me just draw here, remember that each of our reactants, let's say that this is let's say that I'm going to draw GZA2 as just some kind of circle here. And a mole just means a super, super big number. So I'm going to say that this is 1 mole of GZA2, okay? And we need 6 of them for a reaction. So let me make that here. 1, 2, 3, 4, 5, 6. And we're going to react that with 8 moles of CG. But for the sake of this problem, I'm not even going to draw that right now. I just want to say, hey, if I react 6 moles completely, what is that going to give me for my CG2A3? Because that's what this problem is asking about, right? And I know that we're not really solving the problem here. I just want to give you a picture. Well, we can say that it's 4 moles of CG2A3, but remember that this product, even if we get the 4 moles, as in 4 of these circle representations, we don't know if that's going to be more mass or less mass. What if this is more? Which, just looking at it, looked like it's probably going to be more. We got to look at the molar masses though. But what if each of these is just bigger because or more massive, I should say, just because it has a bigger molar mass, right? So there's more mass per mole. That can happen. That happens all the time, right? Each element has its own separate molar mass. So maybe when I draw these moles, I need to make them larger to represent that. Let me make them another color. Now remember, I'm showing that they're more massive, but I'm still going to have 4 moles. So I'm going to make 4 of these. So even though we know that the relationship is 6 moles to 4 moles, right? And we know that just based on a reaction. So we're saying 6 GZA, so that's these red ones here, GZA2, and 4 CG2A3, that's these right here. Well, and I know I haven't drawn everything in the reaction, right? I'm just trying to show you that that still doesn't really help us get from the mass of this side to the mass of this side because we don't know how massive each mole of these is. We have to figure that out. So hopefully that helps remind you of why we can't go straight from the mass of this side to the mass of this side, because we don't have a clear relationship with that just in this chemical reaction. We actually have to look at the molar masses. Now, what we do have a clear relationship is of the moles, right? We know that we're going to have 6 moles of GZA2. We know we're going to have 8 moles of CG. We know we're going to end up with 4 moles of CG2A3 and 3 moles of GZ2, right? We know that. And so what I want to do right now is just let's start practicing writing some conversion factors using equalities showing the mole to mole ratio. So on this side, let's just start and say, all right, 6 moles of GZA2 is the equivalent of 8 moles of CG. And so we're going to turn that into a conversion factor. How do I know that? Because that's this balanced chemical reaction. The chemical reaction is telling you that for each 6 moles of GZA2 that react, you're going to react 8 moles of CG. And so we can actually turn that into a conversion factor, because we can go straight and say, hey, if I've got 6 moles of this, we're going to have 8 moles of this, right? We can do the flip of that. Over here, we can put the 8 moles of CG over 6 moles of GZA2. So let's do the same thing now, but with the CG2A3. And we already sort of illustrated this relationship. So for each 6 moles of GZA2, how many moles of CG2A3 will I have? Think about that for a second. Look at our representation, look at our chemical reaction. What should be on the bottom of this conversion factor? Hopefully you got 4, because here's the 4 moles. The coefficient tells us how many moles are reacting. So for every 6 moles of GZA2 that reacts, we get 4 moles of CG2A3, and we can do the flip of that as well. And then finally, we can do the same thing and relate 6 moles of GZA2 to 3 moles of GZ2. And so we get these conversion factors. Now, we're not going to use all of these for the problem, but this is a good opportunity for you to practice writing these conversion factors. So next, we're going to write more conversion factors. So now we have a way to go from moles of one element to moles of the other element that we're interested in. But that's not enough. As we said, that's great, right? We definitely need that information, but it doesn't give us a relationship to mass. And so next, we're going to write conversion factors relating the moles to mass for the 2 compounds that we're interested in, which the problem is saying we're trying to compare 5 grams of GZA2 and see what mass of CGA3 that's going to give us. So we need to know the molar masses for these compounds and say, hey, for each mole of CG2A3, what will our mass be? What will the grams be? And so for this first one, let's do that. 1 mole of GZA2. And to find this, we need to use our molar masses that's given in our periodic table. Now, I know that the chemistry reference tables will not have these elements because these are made up elements. So you're going to use the ones that are in your slides. So 1 atom or 1 mole of GZ and 2 moles of A2. We're going to add those things up. If we come over here, we get that GZ is 4.003 and A is 54.11, right? And so when we add 1 mole of the GZ and 2 moles of the adrianadon, I don't even know how to say the element that I made up. We all get that. It's a joke because my name is Adriana. Then we're going to get a molar mass, as in for each mole of that, we're going to have a mass of 112.223 grams of GZA2. Now, for these conversion factors, it is really important that we not only include our units of moles and grams like we've been doing, but now it's getting complex enough that you must include the compound that you're referring to or the element that you're referring to. In this case, it's a compound. And that'll make more sense when we get to our final step. So just to reiterate, the way we solved this is we just added the molar mass from 1 mole of GZ and then doubled the molar mass for A because there's 2 moles of it, added those all up, and we got 112.223 grams of GZA2. And again, we can do the flip of that, right? So we can have the grams of GZA2 on top and moles of GZA2 on bottom. And it's just to 1 mole. Okay, then the next one we need to do is for CG2A3. Again, you need to use the molar masses in here. Here's CG, so we need 2 of these and then 3 of the adrianadons. And that is going to give us a molar mass of 1 mole of CG2A3 equal to 210.33 grams of CG2A3. Right, so our molar mass is 210.33 grams per mole. That's the typical units. But again, we learned in our last lesson that we can turn that into an equality and use that equality to create this conversion factor. So if you need some help remembering that, check out the video that we had on the example for writing molar masses. All right, and then we can do the flip of that. So now we have all the tools that we might need. And honestly, we have more than we need, right? We don't need all of these tools, but this is a good time for you to demonstrate to me and to, affirm for yourself that you do understand this. Next thing we're going to do is we need to use dimensional analysis to convert. Basically, this is a conversion problem. I know it doesn't seem like that right off the bat. We haven't seen conversion problems like this. The question said, using the balanced chemical reaction, find the mass of Cg2A3, that's one of these products, that will be produced. That just means that it was created in the reaction, right? That these reactants became these products. So what mass will be produced when 5 grams of GZA2 reacts with excess Cg? Now, what does excess Cg mean? It just means that you're adding enough Cg so that all 6 moles, or I'm sorry, not that all 5 grams of the GZA2 reacts, right? We actually don't know how many moles that is. We're going to find that out in a second. So the problem is just saying you're completely reacting the 5 grams of that compound. All right. And so the excess CG just says you have enough to completely react it. And so what we need to do is go from the 5 grams, and we don't want grams because we need to relate it to the other compound, right? There's no way to do that without converting it to moles first, because again, we don't have a direct relationship between the masses. We don't know the relationship between the mass yet. We need to convert it to moles first, because we know that there's going to be that for each 6 moles of GZA2, we're going to get 4 moles of CG2. So let's start with our given as usual. We're going to take our 5 grams of GZA2. And the first thing we want to do is turn that into a fraction, right? So actually, I guess I shouldn't have drawn these canceling out lines yet, but we'll get, I'll go over that in a second. So the first thing we're going to do is turn that into a fraction. And the way we do that is we take this given, which is 5.0 grams of GZA2, and you divide by 1. That's the rule for anything. You can divide anything by 1 and it's still itself. It's just turning it into a fraction form. Please do not put moles here or grams or any unit. You're not dividing the units out because it's not equivalent. We're saying that we're just turning this value into a fraction. That's all. So we need to choose a conversion factor now, right? And we're going to choose the one that gets rid of grams of GZA2, because we don't want grams, we want moles, so we can compare it to the moles of the other thing. So we need to find a conversion factor with grams GZA2 at the bottom. I'm looking at this one right here. So we need to use this conversion factor, and we're going to cancel grams to get moles on top, and that's what we want. So sure enough, hold on a second. I'm going to put my line, whatever. I'll do the lines again. It's a pain to do them. So let's put this conversion factor in here. So look, actually, this is a perfect time to just put these lines through here. I can go ahead and say, yay, look, I canceled grams of GZA2. I didn't want that. I canceled it. And so now we can do that top and bottom. And remember, the only way that it cancels is if you have it in the top on one of them and the bottom on the other. You cannot cancel them if they're both in the top. That's just mathematically doesn't make sense. You have to divide them in order to cancel. Okay, well, now we've got moles of GZA2, which is great, but that's not our end goal, right? We're trying to find mass of Cg2A3. So we want to just get somehow over to Cg2A3. Now, I already told you that you can't go straight from moles of something to mass of another thing. You have to first do the mole to mole conversion. And what I mean by that is that's the conversion factors we got from our balanced chemical reaction. So we need to cancel moles of GZA2, which is right now at the top. So we need to use a conversion factor that has moles of GZA2 in the bottom. You might be tempted to say like, oh, look, here we go. This one's perfect. But we just go right back to mass of GZA2. That's where we started. So we don't want to use this conversion factor because it doesn't get us closer to our goal of finding the mass of this compound, the Cg2A3. So instead, let's look for another option. We're looking for moles of GZA2 in the bottom. If we use this one here, this will give us moles of Cg on top. So that doesn't help either, right? Because again, we're not looking for, it's not asking us to find the mass of Cg, it's asking us to find the mass of Cg2A3. So this one also doesn't help us. This one over here lets us cancel out moles of GZA2. That's good. And on the top, it gives us moles of Cg2A3. This is the one we want. This is the one that gets us closer to our goal of finding the mass of Cg2A3. So we had lots of choices. We had to find the right one. That's the one that we want. So let me now show that we're going to cancel out moles of GZA2. I'll just copy and paste it here. That's what we wanted. We wanted to cancel out moles of GZA2 and end up with something closer to our goal. And so now at the top here, we have moles of Cg2A3. That's good, but we're not done. We want mass. So now we need a conversion factor that gets rid of moles of Cg2A3 and gives us grams of Cg2A3. And the only one that lets us do that is this one right here. Because this already has moles of Cg2A3 on the top. That means to cancel it, we need moles of Cg2A3 on the bottom. So we can't use this one. This one would just give us moles squared of Cg2A3. I don't even know what that means. So we need moles of Cg2A3 on the bottom. We're going to use this conversion factor here. That brings us over to this one. And that lets us cancel out moles of Cg2A3. And we're left with the units only of grams of Cg2A3. That's what we want. So we have just done a really complex problem and only had to set up one thing without doing a whole bunch of math steps in between. Now that we know we're going to get the units that we want, which means that we're going to get the answer that we want, now let's do our math. So we're going to multiply 5 by 1 by 4 by 210.33 grams of Cg2A3. Remember, we're not using any of these other units because we canceled them out. And so on the top, when we multiply across the top, we're going to get 4,206.6 grams of Cg2A3. You're definitely not done, right? Because we started with 5 grams of something. I don't care what the difference in the molar mass is. Most likely, we're not ending up with 4,000 grams of something. So let's multiply across the bottom now. So we're going to multiply 1 by 112.223. No units, multiplied by 6 no units, multiplied by 1 no units. And if you put that into your calculator, that's going to give you 673.338. And so the last thing we need to do is divide 4,206.6 by 673.338. And our final answer is 6.25 grams Cg2A3. That's exactly what we wanted. Right? We wanted to know the mass of Cg2A3. This gram seems much more reasonable, right? It seems very reasonable that if we start with 5 grams of something and we're going from 6 to 4 moles, so it's fewer moles, but I drew them bigger. And the reason I drew them bigger is because when I look at GZ and A2, GZ has a very small molar mass, so it's not going to contribute a whole lot. A2 is 54.11 times 2, so it's going to be like about 100, right? A little over 100 molar mass. And so even without going through and calculating the molar mass, I looked at this one, Cg2A3, and I was like, oh, Cg has a much bigger molar mass than GZ. A3 of these is definitely going to be bigger because we only had 2 in the other one. So I just drew them bigger from the beginning because I was like, this is probably going to have a larger molar mass. And when we looked at the actual conversion factors for the molar mass, that's what we found, right? We saw that GZA2 had a molar mass of 112 grams per mole compared to 210 grams per mole of Cg2A3. So I would expect, even though we have fewer moles, I would expect that we would have a larger, or at least a slightly larger mass as a product. So this number makes total sense to me. And I do want to encourage you all to do that kind of mental math, right? Like, for example, if one of you got this answer, I really need you all to start thinking like, oh, yeah, this is absurd. I must have done a mistake somewhere, or I must be missing something, because that's the kind of thinking that is really like the real useful stuff that we're learning in this class. Hopefully this helps you complete your problem.